Now that we've learned how to identify the isomer type and decided that the possible type that we're looking at is an optical isomer, now we're going to do some practice problems deciding whether something's an optical isomer or the same compound. For each of these sets of molecules, I want you to do two things. First, I want you to find the asymmetric carbon. We're going to highlight that. And then the second thing I want you to do is decide whether this set is an optical isomer or is the same molecule. We'll start by finding the asymmetric carbons that are in each of the following compounds. So please pause the video while you find those asymmetric carbons and then restart it and I'll go through them with you. Let's start with set A. So I'm going to look at the first, just the left-hand molecule, so we can just focus on that one. And we're going to see that the first carbon here has a CH3 group. Well, CH3 has 3 hydrogens. Those are all equivalent to each other, so that one cannot be an asymmetric carbon. The next one up, where you see all these dashed lines, that one has a CH3, it has an OH, and it has an H. There's definitely 3 different groups. Now the fourth group is a CH2CH3. That is different from just a CH3, so that is a fourth group. That makes this one an asymmetric carbon. Now we're going to go up from there. We're going to ignore the OH and the H because they're not carbon, so they're not going to be asymmetric. We're going to go up from there. We're going to see a carbon with 2 hydrogens on it. As soon as I see those 2 hydrogens, I know it is not asymmetric. And the last carbon on here has 3 hydrogens, so again, it is not asymmetric. Now if we look at the second molecule, you'll see exactly the same thing. We have the CH3. It's on the other side, but it's still a CH3, so not asymmetric. This carbon with the stuff hanging off is definitely your asymmetric carbon, and the other 2 are not asymmetric. Let's look at B. Now on B, we have 3 carbons to look at, so we'll start at the bottom. That one has 3 hydrogens, so that one is not asymmetric. The middle one has a hydrogen, an OH, a carboxylate group, and a CH3 group. So those are 4 different things, so that one is your asymmetric carbon. And we can see that also in the other molecule, that is also an asymmetric carbon. Now we'll go to the top one. That has 2 bonds to oxygen and another one to another oxygen. So we definitely do not have 4 different things on there because 2 of the bonds go to the same oxygen. So that one is not asymmetric. So we have only 1 asymmetric carbon in letter B. Now let's look at letter C. Now that's got a lot going on, but let's look at it carefully. Starting from the left-hand side, we see a CH3. That is not asymmetric. The next one, you don't actually see the carbon, but we know that those bends mean there's a carbon there. So it's a carbon, and it has 2 hydrogens on it. That is not an asymmetric carbon. The next one has the group that we just looked at. It has a hydrogen. It has another group, one of them with an OH, and it has a CH3 group. That is an asymmetric carbon because we've got 4 different things attached, so that's an asymmetric carbon. Let's look at the last one and see if it's asymmetric. So if we look at that carbon, it has 2 hydrogens here, so we know right away that that one is not asymmetric. And again, we see the same thing with the other molecule because these 2 are matched sets, so you know that we'll have not asymmetric, asymmetric, and not asymmetric. So now let's look at letter D. When we look at D, we see the first one has a CH3, not asymmetric, a CH2, not asymmetric. We see this one that kind of looks like it might be asymmetric because it's got all that lines on it, right? That kind of gives you a clue. Let's look here. And so that one is asymmetric because we see a CH2, CH3, we have an OH, we have a hydrogen, and we have a CH3. And the CH3 is not asymmetric because it has 3 hydrogens. And we see that again on the other structure. So we see just 1 asymmetric carbon in letter D. And we're going to go down. We're going to look at letter E. We're going to see that we have this benzene ring. Benzene ring is not an asymmetric carbon. It has double bonds. It cannot be asymmetric because there's not enough attachments to any one of those carbons. So all of those are not asymmetric. Then we go up from there. We see a CH2 because we see 2 hydrogens on there. So that is not asymmetric. And the next one is asymmetric because we see this benzene ring hanging off of one side, an OH, a hydrogen, and a methyl group. So that one's an asymmetric carbon. And the last one is our methyl group, which has 3 hydrogens, so it is not asymmetric. So we only have 1 asymmetric carbon. Even though there's a lot of stuff there, there's just 1 asymmetric carbon. And again, the other one matches. We can see that this is the only asymmetric carbon. And now let's look at letter F. For F, we can see the benzene ring, again, no asymmetric carbons. The CH2 going up, not asymmetric. The next carbon, looks like it has a benzene, a CH3, and a hydrogen. And we see this 3rd carbon chain, but it does not have a benzene ring, nor does it have a methyl group. So it looks different, and so we know that that is our 4th part. It looks like that one's asymmetric. And then we go up from there and we see that we have a hydrogen, and we've got this big group going down, and then we've got something to the left and something to the right. Now those are both CH3 groups. Remember, they have no ending there, so that means it's telling you it's a CH3 on there. So those are both the same. It doesn't happen to be a hydrogen, but the CH3s are the same, so that is not an asymmetric carbon. And again, because those are CH3s, those have 3 hydrogens, are not asymmetric. And we see the same thing over in the second part of letter F, where we have only 1 asymmetric carbon, and that's the one down below. And that is all of the asymmetric carbons. Now you need to go back through and see which ones are optical isomers and which ones are the same isomers. And then I'm going to see if you can find, there are 2 of them that are matched on here. So there's another one of these molecules that has the same formula. They're both the same compound, just written in different formats. Because it's a little more difficult to decide if it's an optical isomer or the same, I'm going to do each one individually. So we'll start with just A. After you return, we'll go over A, and then you can pause the video again for part B. For set A, we're trying to determine whether we have an optical isomer or if these 2 molecules are the same molecule, just drawn a little differently. So they appear to be different, but they are still the same molecule. And the first step in this process we've already done, which is to identify the asymmetric carbon, which we found here. In this structure, you should see that the OH is pointing towards you, the methyl group is going back, and the hydrogen is going back and away from you, off to the left and off to the right, but they're still both going away from you, and that the ethyl group at the top here is in the same plane as the asymmetric carbon. So this is a 3-dimensional structure. It's a little harder to see, but this is a 3-dimensional structure. And then what we want to do is see if the other one is a mirror image of it, or if we can rotate it to make it the same or a mirror image. So we're going to start with just looking at each part of it. We'll see the CH3CH2 part is a mirror image. Notice that I don't write the letters backwards, so the carbon will still look like a carbon, but it is going to be a mirror image. So that part is. In that part, it doesn't matter if I have the CH3CH2 mirrored or not. It would still be okay, even if it wasn't, and I'll show you what I mean by that here. Down below, we see that we're looking at the asymmetric carbon. That's the only one we have to focus on. And what you should see is that the 2 hydrogens are close to each other, so they are mirrored. The OH is basically just coming forward, and that the methyl groups are pointing away from each other, and so they are mirrored. That tells us that these are mirror images and that this is an optical isomer. Please pause your video and try letter B. Again, see if it's an optical isomer or if these are the same molecule. And we'll see that we have to find that asymmetric carbon, which again we found earlier is this carbon here. We're only going to focus on that, and we're going to see that the 2 OHs are closer to each other, the 2 hydrogens are pushing away, our CH3 and our COOH are in the same position, so this is a mirror image, and that makes this an optical isomer. Now this one's a little bit trickier because you can't see what's going forward and back, so let me draw those in for you. Everything going vertical is going away from you. Everything in the horizontal lane is coming towards you, so they should be bolded. And in this case, we have nothing that's in the same plane as the carbon that is asymmetric. And pause your video as you try letter C, and then when you return, I'll show you the answer. The first part of this, you should find the asymmetric carbon, which we found earlier is this carbon here. And we're going to compare it to see what happens here. So you probably noticed right away that this is not written as a mirror image. It looks more like it's the same. But let's look at it a little more closely. We have to look at those bold lines, dashed lines, and solids and see which way are they going, and are they all in the same places. And we should see that they are not. Still doesn't mean that it's an optical isomer, nor does it tell us that it's the same until we actually compare them. So I'm going to make it a little bit easier to look at by, instead of using the whole structure as is, I'm just going to put in the numbers 1, 2, 3, and 4. In more advanced classes, we would tell you which ones were numbers 1, 2, 3, and 4, with the number 1 being the highest priority and the number 4 being the lowest. Generally what we do is we just make it, the most busy one is number 1 and the least busy one is number 4. So we just kind of make it simple. So in our case, we're going to put this one with the alcohol is going to be position number 1. We're going to write that on both of these molecules. And then number 2 will be just kind of this longer group, this ethyl group, and that'll be number 2. And then number 3 will be the methyl group, and the least busy one, or the least interesting one anyway, is the hydrogen. It doesn't really have anything but hydrogen on it, so that's going to be our number 4. And now we want to make sure that we have our bolds and dashes in the same pattern that we see up above. So again, when you first look at this, it looks like we have the 1, 2, 3, and 4 in the same 4 corners. But what you should notice is that in the first molecule, number 4 is going back and number 2 is in the plane. Whereas in the second molecule, number 2 is going back and number 4 is in the plane. So those two have switched places. Let's see what kind of effect that has. So what we're going to do to see the effect is we're going to have to do a rotation so that they're all going this correct direction, forward or back, as we need them to. So right now, the methyl group, number 3, is pointing forward, and we want to keep that one that way. And it looks like number 1 is in the right position because it's going in the right direction. So let's get it so that both number 2 and number 4 are in the correct places. Without breaking bonds, we can only rotate the molecule. If they are the same molecule, we should be able to rotate 3 of them to get them in the same relative orientation, forward, back, or in plane, as they originally were. To help me do this, I'm going to grab number 3, and I'm going to spin the other 3 around where number 3 is. So we're going to just do it on the second molecule to see if we can get it to match the first molecule. You can spin it in either direction, but I'm going to spin it in the clockwise direction just because it's easier for most people to follow. So that's just to help you out. So let's go ahead and rotate it. Again, we're only doing the second molecule as we rotate it. We'll look at number 1 first. So it starts in the upper right-hand corner and it drops down to the lower right-hand corner. And then that pulls number 2 with it, and number 2 now is in the upper right-hand corner. Both of those are in the plane. And number 4 goes to the upper left-hand corner and it goes to the back. At this point, it doesn't look like they're the same or mirror images. So we're going to try another rotation. Now in this case, what I want to do is I want to think of number 3 as if your foot were on the ground. Number 4, your foot is up in the air behind you. So your number 3 is in front of you, number 4 is behind you, and you're holding your arms off to the side. Now we're going to set down number 4 so it goes straight down. And as you do that, number 2 will rise up, and so will number 1. Now let's see what happens. And now you should see that number 3 is still in the same position. Number 4 has dropped to the other side. Number 1 is in the plane on the right-hand side, going up, and number 2 is in the plane on the left-hand side, going up. So you can see that these two are exact matches and not mirror images of each other. That means that these are the same molecule. On my tests and quizzes, you will not be expected to do problems that are quite this difficult. They will be definitely easier ones, like you saw in questions A and B. Okay, for letter D, please pause your video, check this out. When you're done, come back and I'll tell you the answer. Okay, welcome back. So the first thing we need to do is identify the asymmetric carbon, and we see them here and here. And now we want to decide if this is an optical or mirror image, or if this is the same compound. In this case, we're going to put the mirror right down the center, and we're going to check to see if the CH3s, they match just fine because they're going in the plane, so we don't see a difference there. We do see that the hydrogens are going back and away, but they're opposite, they're close to each other, facing that mirror. The OH, similarly, is close to each other. They're coming forward, but they're close to each other. And then we see the ethyl group, the CH2, CH3, are sticking away from each other. So this does appear to be a mirror image, and so we would say that these are optical isomers. All right, let's look at letter E. Now this one's a little bit different. I'm going to show you the answer right away. I'm not going to have you pause this one. And that's because I'm going to show you a trick in how to look at these. First, we need to find that asymmetric carbon, and we see it here and here, as we saw before. Now I wanted you to focus on here is the fact that these are drawn in exactly the same way. So we have this benzene ring going down, and it's going to the back, and then we see the OH is pointing up and forward, and then we have the two that are in plane are going off to the sides in exactly the same positions. In this case, the first one and the second one, what I see different is the H and the CH3 have switched places. Anytime that any two of them switch places, and again, this has to be in the same model, so you see them drawn exactly the same. Anytime those two switch, we must have an optical isomer. It's going to be a mirror image, and you can rotate it to the point that you can see it as a mirror, but for the moment, I just want you to recognize that when I switch those two like that, these are optical isomers. So what happens if I switch 3? Well, then we switch it back again. So you won't only see 2 of them can change at a time. All right, so let's look at letter F. Go ahead and pause your video while you try to figure out whether this is an optical isomer, mirror image, or if it is the same molecule. And welcome back. First, we'll mark those asymmetric carbons so that we know which ones they are, as we've done before. And those are here and here. So hopefully you saw from our last one that these two have switched places, and so that this one is an optical isomer. And for this last one, this is a summary of all of the ones that we looked at, and you're going to be looking for which 2 of these, A, B, C, D, or E, or F, are the same question written with different structures. So see if you can find that. Pause your video while you look this over, and then when you return, I will provide you the answer. To identify the sets that have the same molecules, we'll need to look at the structures carefully. The 2 that look the same right off the bat would be E and F, so let's look at those 2 first. Notice that they both have that benzene ring, and they both seem to have the same number of carbons. But letter E does have an OH, and F does not, so those 2 are not the ones that match, and they don't match anything else because nothing else has a benzene ring, so that makes it kind of easy. Similarly, if you look at letter B, it has something with a carboxyl group, the COOH. Nothing else has that, so we know that that one does not match the others. So let's look at the rest of them. First, let's see if they have the same number of carbons and the same functional group. So first we'll do functional group. It looks like we have an OH on everything. And then let's count carbons. So it looks like A has 1, 2, 3, 4 carbons. C has 1, 2, 3, 4, 5 carbons. And D has 1, 2, 3, 4 carbons. So it appears A and D are closer to each other than C. C has too many carbons compared to A and D. So now let's just check that those OHs are on the same position. And it looks like yes, both A and D are 2-butanol. Hopefully that'll help you to identify the optical isomers.